Well, hello, everyone. In the interest of time, I'm going to go ahead and get started. I'm Quentin Bailey, by the way, professor in the physics department. I'm standing in for Dr. Prodden. So we have our last session of undergraduate capstone talks. We have quite a few folks speaking today, and it will be like lightning talks. So 5 minutes plus 1 minute for questions. So we're trying to squeeze everyone in there. So I'm going to go ahead and get started. So our first speaker is Sammy Flores. And she's going to be talking about quantifying the outbursts of the BE star QR vol. Told it's pronounced vol. Okay. Do you have a mic?
Hi. Okay, can you guys hear me? Okay, cool. So I'm going to be talking about my research on quantifying the outbursts of the BE star QR vol. And first, I would like to say thank you to Dr. Noel Richardson for guiding and supporting me through this research project. Okay, so first, we have to understand what BE stars are. So these are rapidly rotating non-supergiant B-type stars, and they eject gaseous material from themselves to form a decretion disk. And they can have either a steady state disk, or they can go through multiple outbursts which lead to a disk forming and dissipating after a period of time. So now we can talk about QR vol. So QR vol is a star that goes through many, many outbursts, and like I said, those outbursts form a disk that dissipate after a period of time. And the top plot here is showing 2 lines that I just picked from the many, many files of data. And it's showing absorption and emission spectra. And I have a line going through where the H alpha wavelength is, which is what we're focusing on. So what we did was look at data from the past 20 years or so from the BESS archive. And I plotted that in the plot below. And we could identify at least 5 large outbursts from this. So here we have an exponential decay formula. And this, what? Oh, okay, cool. Okay, so exponential decay formula. So this helps understand the disk's viscosity parameters, and I use this to fit my data using a Monte Carlo code that I developed. So with that equation and my Monte Carlo code, I was able to model the dissipation of at least 1 large outburst. So from the 5, I mainly focused on the second one, mainly because it was the easiest to work with. And I did have to take out some points from it due to some of the values being out of the range that we see in our y-axis for equivalent width. So this lasted about 2 to 3 years. So I was also able to produce a corner plot, which unfortunately is not our best due to the model being so limited and our disk being active during the outburst decline. So yeah, this is supposed to show our best fit of our parameters, which still have very large errors, but as you can see, there's very elongated contours, which mean the parameters are dependent. So if I change one, the other has to change. Well, now we have a 2024 micro outburst that happened, which is very exciting. So this here is a plot produced by Jonathan Labadie-Bartz, which holds data from the Las Cumbres Observatory as well as our own and the NRES spectrograph. So this here lasted about a couple days. One thing about QR vol was that it wasn't considered periodic until I ran it through period 04, and I performed a Fourier analysis. So we have a potential period of like 4 years. So, and that's all the data that we gathered. And next steps for this research is that we're going to write and publish a paper with the results we've seen here today. Thank you.
Are you saying that the outbursts are periodic?
Yes.
Is that common?
For QR-Vol, it wasn't. It wasn't considered periodic for a while until we ran some of the new data through Period 04, and it seems like there is a periodic timeline. Oh, this way. So this is basically that equation I showed. It's just showing how long it takes for it to kind of go away, I guess. But that I was able to use the Monte Carlo code that I developed to run through some of those parameters, which is, the time it takes for it to completely go away, the amount of days, and the peak of, or the value of the peak for each outburst. So each outburst is represented by a peak in the data. So, yeah.
Okay, so next up is Haley Beyer. And she'll be talking about probing the multiplicity of dusty, carbon-rich Wolf-Rayet stars with high-resolution near-infrared spectroscopy. Okay, go ahead.
Thank you. All right, so I'm Haley Beyer. I will be telling you guys about the research I've done with probing the multiplicity of dusty carbon-rich Wolf-Rayet stars with the high-resolution near-infrared spectroscopy. And I would just like to say thank you to Dr. Richardson for putting up with me for these past 3 years and helping me, guiding me along with this research. So WCD stars are the main types of stars that I am focused on. They are evolved massive stars stripped of their hydrogen, extremely hot, and have the possible formation from strong stellar winds or binary interactions. These stars can either be nitrogen or carbon-rich in their winds, and some of these WC form dust, which have been discovered through infrared excesses, and imaged at large scales with ground-based infrared imaging as well as JWST. So for their dust formation, it has been seen to be constant, periodic, or even episodic in nature. And the underlying question for episodic dust makers are they really just periodic dust makers? Because they have that potential for win-win collisions to begin their dust formation processes. WR140, which is seen in the background of all of my slides, and imaged by JWST, it has a well-known orbit, has been used to create geometric models of the dust creations like those rings in the image, and it displays how well the binary orbit contributes to the dust creation. So it is a kind of fundamental basic star that we can kind of base all of our survey off of. So getting into the survey, I conducted a IGRN survey of the galactic CD stars using the IGRN spectrograph. Most of the data has come from the Lowell Discovery Telescope as well as Gemini South Observatory. This is the first known spectroscopic coverage of the WCD stars in our galaxy. And we are looking at the key companionships, or using their spectra to look at the emission and absorption line to determine if it has signs of an O or B type companion, beginning to probe the multiplicity of these objects. So here's a list of all of my sample stars. Most of them have been in the H band as well as the K band, but today I'm going to focus on the H band. And so far we have indicated that each of these systems that we have analyzed, we see an obvious sign of a binary companionship in the spectrum. So here is WR119. In the H band, that top plot is the overall spectrum, and then the middle plot of the first subplots show the absorption dips confused right now. That's okay. So the middle subplots show the binary companionship with it, whereas the bottom subplots, the last three figures, show those emission lines indicating the WR features of the system. So with those emission and absorption lines, we see obvious signs of a binary companionship. And then for another example, WR77AA, which again, that top plot is the spectrum where we cut subplots from it. And again, it shows the top subplots of the binary companionship as well as WR features. So throughout all of these like 20-some plus stars that I have, we have been able to indicate that all of these stars have a binary companionship. While some of the data have not been such high quality, they have already been well-established binary systems, so we can conclude that all WCD stars have a binary companion, and it is a key factor in their dust production. Any questions?
I'll ask you a quick question. Can you go back to the these plots? So what was the feature you look for to know you have a companion here? What was
If I'm not mistaken, and my brain is really muddled right now. Thank you. If I'm not mistaken, and my brain is very muddled right now, but it is the absorption dips that indicate the binary companionship with it. So where we see the dips on the two plots, if I can bring the laser out, maybe. These dips here and here show those binary companionships where like the emission lines where they spike up kind of give us the Wolf-Rayet type feature of the system.
I'm not sure if I'm understanding this completely correctly, but does the binary companionship, does that tell you anything about how like the dust production might be periodic in nature, or?
So that's a great question. The binary companionship, if we look at that figure, it forms with the shocked wind front. And so having that binary companionship with it helps definitely create that dust production with it. So where we get like the geometric models, like with the background of those rings from WR140, it's just when those two stars get close enough together to form that shocked wind front and produce that dust off.
All right, thank you. Let's thank our speaker again. And now we have our second Haley of the day. Haley Murray is talking about her work with some crazy professor, I don't know who. Physics beyond GR, space-time symmetry breaking, and black hole solutions.
All right. Hi, everyone. As Dr. Bailey said, my name is Haley, and I have been working with Dr. Bailey over the past several years on this project looking at bumblebee gravity and spherically symmetric black hole solutions. So I kind of wanted to take a more broad approach to this talk and talk about my journey through my project and how to do a theoretical physics project. So my project first started with background reading and exercises in Schutz's GR. And then from there, I derived some solutions as an exercise. So this included the Schwarzschild solution, one solution where there was a scalar field in spacetime, which I never actually finished. So it's okay if you don't always finish the exercises that you set out to do. And then finally, I derived the Reisner-Nordstrom solution, which is a black hole with charge. And all of these helped prepare me to start with investigating a model beyond general relativity, which is the model we are working with called the bumblebee model. So this model generalizes Einstein-Maxwell theory, And it adds a vector field in spacetime that causes spontaneous spacetime symmetry breaking. So those are the field equations right there that describe how matter and energy are distributed in spacetime. So in this project, we assumed a static and a spherically symmetric solution, and with those assumptions, we arrived at the following coupled nonlinear ODEs. And so from here, what my work involved doing was both pen and paper work and computational work. So with those general field equations, without making some simplifying assumptions, we didn't find any nice analytic solutions, but we were able to find some specialized exact solutions under particular assumptions, which I'll mention later. And then additionally, I did some computational work. So this is using numerical solvers to solve the field equations, and also with those solutions, solve the geodesic equation to find trajectories of photons around the black hole. And that was done with Mathematica. Okay, so now getting into some of the results of the project. So for the specialized exact solutions, we had this assumption that A and B, which are components of the metric, if we assume that AB prime is 0, we find the following specialized exact solutions, which actually include the Reisner-Nordstrom solution and the Schwarzschild anti-de Sitter solution, which is pretty cool. And there are a lot of branching trees of assumptions that you can make along the way, so that's kind of outlined in this flowchart right here. And then additionally, so this was kind of towards the end of my project, so there's a lot more investigation to do in here. This could be a whole separate project, but I used Mathematica to solve the geodesic equation to find the trajectories of photons around the black hole in both in general relativity and in modified space-time to kind of compare. So in the plot on the left, you can see a photon trajectory in GR, which is the dashed line, and then additionally in this modified spacetime, where we assume that the potential that goes along with this background field takes the form of a hypergeometric function, and we see that the photon would have a different trajectory. And then the plot on the right, these are all in modified spacetime, and this was just looking at different initial velocities. So there's lots of work to do here, looking at different initial conditions, initial positions, when your potential takes different forms. There's a lot to explore, but that's what we've gotten into so far. So a paper with Dr. Bailey, Dario, and I is submitted to Physical Review D as of the last few weeks, which is really exciting. There's the archive number if anyone is interested in looking at the paper. And I just wanted to thank Dr. Bailey for all the support over the last few years. Yeah, I've learned a lot, and it's been a great time. There are my references. And that's all. Are there any questions?
What does geodesic mean in this context?
Oh, okay. So the geodesic equation, it kind of describes the path that photons or particles will take, and you can think of it sort of. It's kind of the analog of the shortest distance between 2 points is a straight line. It's kind of the analog of that, but for when space-time is curved. I went fast. Oh, the anti-de Sitter solution, if I go back to here, so the anti-de Sitter solution is those first two solutions on the flowchart, which are to the right of the boxes. Those, I actually don't know too much about de Sitter and anti-de Sitter spacetime, but it's something that there's been a lot of research in recently, and I know it has to do with string theory.
On page 9,
Yes.
on the left,
Oh, yep. Mhm.
the Reisner-Nordstrom charged black hole trajectory has like a sharp corner. What's going on there?
Oh, I think that's the non-GR one. So that would be the one with the extra potential. So I don't have a good explanation as to why it would have that sharp turn in relation to what like the form of the potential is, since it takes the form of a hypergeometric function. I don't see any clear connection there, but it was quite interesting how so the orbit of a photon in the Reisner-Nordstrom case, there is one place where it has a stable circular orbit. Well, it's unstable because it's at the maximum, but it was really quite interesting with this hypergeometric potential. There were several different initial radii which produced a stable orbit. So there's something in the space-time going on there that that makes it so that those different orbits are possible. But
Okay, so our next speaker is Kaya Schuderman. He's going to talk about distributional methods for detecting gravitational waves from core collapse supernova. The word core collapse supernova tells me who your mentor was.
Cool. Thank you. Yeah, so this is the work I've been doing for the last couple years with my mentor, Dr. Zanelin, and another student who is in Daytona, but she's graduated now, Alani Miyoko. Yeah, so we're looking into data analysis on core collapse supernova, but a distribution of them rather than just one, because we've never in LIGO discovered gravitational waves from any supernova yet. So what happens first whenever we see a supernova in the sky is we ideally detect something on our detectors up there, the one in Livingston and Hanford. And from that we get some gravitational wave strain over here. It's just a bunch of shaking on them. We then throw that into an algorithm we call coherent wave burst, which from the time frequency plots of the gravitational wave strain, we determine some sort of measure of the energy of the event, which we call a rho. And instead of just getting one rho per supernova, which would be great, we get a bunch of them. We get a huge distribution of them, all with a ton of different powers. And typically what's done in LIGO is we look at the most powerful one and decide if it is or is not a supernova. And we've never been sure enough so far to say that any have been. So the point of this project is to, instead of looking at the loudest one, do something similar to what they did with the Higgs boson over here and look at the shape of the distribution, something that's looking at the effectively the curve of it rather than just any one point. And so yeah, that's the point of the project up here at the top, is to determine if this method can have any different results than just the loudest event approach. Whenever I say distributional methods, what I mean here are these four bold tests that we have here. And what they do is we have two distributions of events, just a bunch of numbers in a list, and compare them against each other. And these are supposed to all decide if they are or are not the same distribution. And they all do it in different ways, but we have no way of just outright ruling out any of these tests, so we have to do them all and see what works the best. There's also this other thing at the top, this Feldman-Cousins method, which is just a counting method. We sort of use that as our lower limit. Hopefully it works less good than our methods. So yeah, here's something that we came across in the project first, is that instead of having 10 to the 3 events, we wanted far less to do these on. So we came up with a method of cutting out a lot of the really quiet events. We say if these triggers are too quiet, we just should not be able to detect them outright, and so we just throw them away. And we have an approach here that we follow to say what that limit should be. That depends on how good our detector is at the time. Another thing we came across is these tests that we use whenever they were typically tuned for a 5% false alarm. We weren't getting that. They were overperforming, which is actually bad. So they were giving us probabilities whenever just compared background to background, no real triggers in there. These are the same distributions. They were only saying that they were the same one about or less than 5% of the time, so we had to change that and make it so that our our average false alarm, whenever the test isn't working correctly, is 5%. And that's just a rule of thumb number that's used in a bunch of papers, similar. So we changed that. We tuned it so that they work better. Yeah. So next are our methods for the test. Here's sort of what we do. We have a big distribution, which we call the mother distribution. It's basically, I don't know if I say it. It's something like 1,000 years of background data, which we get just by. Oh wow. So we get a lot of background data and then split it up into 2 smaller distributions, and then throw our injections into one of them, and then see if our tests alarm or not. And so we did that in the beginning with these point injections, which are just numbers that we're throwing in there to one of them, and we see, which was the biggest deal for us, it works. It sort of works. Whenever we have injections, they alarm more than 5% of the time, which is great news. That means that there's something here. And so you can see these little pictures. It's sort of working. And then so from that, we also wanted to do what we call modeled volumes. Instead of just throwing numbers into a list and saying if it works or not, we wanted to do something physical. And so into our background data, we ran a bunch of supernova injection runs through the typical LIGO pipeline. And then these were the waveforms that we throw in over here. And so these are just the typical ones that LIGO uses in their real search. And then we also did that along a bunch of different distances. So instead of just injecting them all at the same amplitude, we varied it over real stars where they exploded at and injected at those distances. And that's basically what we're trying to get at here. And so the distances affect the rose power over here. What we still need to do is make the plots for that last bit. We haven't run them into the test yet. They're all run on the coherent waveverse side, so all the LIGO stuff is done. It's just now actually running them in our tests. And so making the plots for that, and then writing the paper, doing all the things. Yeah. Thank you, guys. That was my...
I find it very interesting that many of our graduates and many of you are experts at all these statistical methods of analysis. Okay. Industry likes that, in case you want to go to industry. Thank you. Okay, so next up, Brandon Pillen. Brandon's going to be talking about mock setup of Newtonian calibration characterization for laser interferometry.
Hello, my name is Brandon. I'm going to be talking about mock setup of Newtonian calibration and characterization for laser interferometry. I wanted to thank Dr. Michele Zanelin, my mentor, as well as his grad student, Joshua Freed. So first, what is a gravitational wave? A gravitational wave is a disturbance in space-time that stretches and squeezes space, as you see in that animation. And here is our setup of LIGO. So we have our gravitational source on the top left. Is that yes, that's left for you. And then we have our LIGO in the bottom right. And what I'm going to focus on are the 4 mirrors, 2 on each axis, so the positive x and the positive y. So from LIGO, we get this strain data. So this is how effective we are at detecting events, gravitational events. So we can see on the far left, when we have a low frequency, we are not very good at it because we have a high strain. So that means that the suspensions themselves move a lot, and we want them to stay as still as possible. So to do that, to improve that, we have a different project, not my thesis, where we are testing, designing, and adding control systems to a pendulum. That is this pendulum on the left That is the LIGO pendulums on the right. You can see they're a lot more complex than ours. We have what's called a Cavendish pendulum or a torsion pendulum, where it just rotates in, I think it's the yaw direction, if anyone remembers what that means. And we are modeling that type of rotation. And from that, we get these equations for the natural frequency. These are the eigenvalue equations. So we have S, which is the eigenvalue, large gamma, which is the frictional force, or the frictional term, and then omega, which is the natural frequency. Then using that pendulum, we're going to apply this force equation, which is simulating a gravitational force on that pendulum. Kind of, that's not really what I meant to say. I meant to say that we have this rotor on the left. Oh my God, it's your right. On the right. And we're going to apply that with a gravitational force on some pendulum and see how that affects our pendulum. So to do that, we have this measurement apparatus. We have, starting in the top left, our laser. This top laser is for the LIGO, is to mimic the LIGO laser and how it reflects off of the masses. Then we have the second laser, which is we're going to use to measure the angle of our pendulum. Then we're using 2 photodiodes in the lower left to tell how far the pendulum has spun. So our current results from a physical source is this graph. Some of you might find it familiar. I've put it up a lot. And it uses that complicated fit function where it's a sinusoidal wave with decay. So we have some sort of friction, and if we bump it, it'll oscillate like we expect, and then it'll slowly stop oscillating. We just get noise. That's what that the right side of the graph is. And sadly, I wasn't able to get data inside of a vacuum chamber, so I had to model what my pendulum would look like. So this is a check to make sure that my pendulum is working. So I have some initial condition. I have that same shape as before, if you can recognize it. It's that decaying sinusoid. And then on the bottom, we have the Fourier transform, just to say what frequencies we have a lot of. Then here, this is what I did a couple days ago, where we apply that force function to our differential equation to show how our pendulum will react to that external force from the NCal rotor. And so this shows if we have our pendulum stationary and our NCal rotor at 30 degrees at some distance away from our pendulum, then, and it's spinning, then we get this very weird function where we get a high displacement in the beginning, and then it oscillates in a more even pattern later. And what's great about this is that we can find that we have a huge spike in our frequency domain on this Fourier transform on the bottom. And that means that if LIGO uses something similar to this, they can use that frequency spike to calibrate their detector, which is awesome. And in the future, I want to use the vacuum chamber and have some sort of real physical data instead of just modeled data. Thank you very much.
Hi, Brandon. Can you go back to the first graph you had with all the blue points? So, one more. Yep, there we go. You said it's decay, and it looks like it's decaying, and then you got that jump over by 35. Do you know what's up with that?
Short answer, I have no idea what's going on there. What I expect is happening is that we had a bunch of noise sources that all combined together and just happened to make a spike.
Okay, our next speaker is Jacob. Jacob Banna, and he's going to talk about correcting the background sources found in the LIGO interferometer and data quality testing.
Thank you. All right, so I did my thesis on correcting the non-astrophysical sources found within the LIGO interferometer. So a little background vocabulary for the uninitiated. An interferometer, specifically a Michelson interferometer, is a device that we use to detect gravitational waves. In its most basic sense, it's a laser that's fired into a beam splitter, and this splits the beams into two arms, and the mirrors at the end of each arm reflect it back and create an interference pattern, which is what we are able to use to detect gravitational waves. The one that we use is the Laser Interferometer Gravitational Wave Observatory, or LIGO. There are two in the United States. The data I used for this was in Livingston. And a gravitational wave is a distortion in space-time that we detect with the interferometer. It is caused by large or very violent events that happen in space, like two black holes colliding or a supernova or things of the like. On your left is a interference pattern. This is not the one used by LIGO, but this is just an example of what it might look like. And on your right there is how we look at the data. That's an example of the first detected and confirmed gravitational wave. You can see that it has a baseline, and then eventually it wiggles until until it stops. This is from two black holes colliding, and it resulted in a 60 solar mass black hole, I believe. All right, so the point of the work I'm doing is to find the best auxiliary channel out of the 6 channels that I did to use and measure, not measure, we're supposed to look at the efficiency of code that removes loud sources of gravitational wave candidates that are not from astrophysical sources. So this is a resultant histogram, not a histogram, but a graph of all the gravitational wave candidates. This is before. All the dots you see are candidates that are within the data, and especially the darker ones are the ones we're looking at. Those are the ones with high SNR. They are very loud and very likely to not be actual gravitational wave sources. This is after the code that I used was applied, so before, after, you can see a whole lot of the loud noises were removed. Okay, so what we are looking for here is a very high maximum efficiency over dead time. The efficiency is the percentage of data that was removed from the data set, and I didn't write it here, but the percentage of data that was removed is not the total set, it's the very loud sources above an SNR of 300. So if we look at the first one, the POP, which is the one that is currently in use, it has a very high maximum efficiency over dead time with a very low dead time, which is what we want. Dead time is the amount of time that is removed from the data set entirely. And so for now, it looks like the one that is already in use is the best option for us, but a nice backup one would be the one at the bottom, Transmons YB, which has a 62.21% efficiency, and the dead time is 0.72, which is pretty low, which is what we were looking for. All right, thank you.
Can you go to the slide right before this one? Yeah, could you explain a little bit about the last column, LF?
So LF stands for the low frequency threshold. It's just a parameter that we used when we, before we initiate the program. It's just something that we put in there. It's the lowest frequency allowed for the program to measure it or to process it. So yeah, that's just a cutoff point.
Sorry. Is there a reason why it's different for the first two channels versus the last?
Yeah, so whenever we iterated through the channels, we just moved these settings around just to find the maximum efficiency over dead time for each one and to see what the best data we could get for each channel. The best ones I found were represented up there.
I know you said that this data was from Livingston, correct?
Yeah.
Is there any like future work to do to like compare like the same models against this data at Hanford just to see if there are like discrepancies between them? See if one works better at one place versus one works better at the other, then choose, or will you just pick one from the data you got here and then just like apply it directly to the same stuff over at the other site?
So I think what I did only really applies to the Livingston one, but I'm not entirely sure.
Time to move on. Thank the speaker. Very good. Our next speaker is Jerome Busquin. I don't know if I butchered your last name or not. And actually, this looks quite interesting, ground-based contrail observation, as opposed to that crackpot chemtrail thing. Contrails.
Thank you.
Okay. My name is Jerome Busquin, and over the past year, I've been working on ground-based contrail observation. First off, I'd like to say thank you to Dr. Zanlin for letting me do this work, and then also to Google Research, Breakthrough Energy, and Western University for collaborating on this. So first off, what are contrails? Contrails are made of ice crystals that form when an aircraft passes through a supersaturated region, where the aircraft exhaust provides condensation nuclei that allow for water vapor to latch on, allowing for these persistent artificial cirrus clouds. So why do we care? Well, 3.5% of all global climate impact is caused by the aviation industry, with half of that being contributed to by contrails. So it's a very significant impact. And why this is because these contrails are trapping outgoing long-wave radiation that the Earth is trying to emit. What makes this more interesting is that these ice supersaturated regions are relatively thin, allowing for aircrafts to change altitude and to not produce a contrail. So this provides a very cost-effective way to reduce the aviation's climate impact substantially without making any major changes to the industry as a whole. However, there's an issue that there lacks significant validation of these contrail prediction models, and that creates a strong need for a data set that validates with ground truth what we're predicting. Current observation methods use geostationary satellites, which Google has worked on extensively. And the benefit of geostationary imagery is that it has a very high temporal resolution, so every 10 minutes we're seeing an image. And it also allows for us to see exactly how much the climate forcing impact these have. However, the issue with geostationary is it doesn't have the spatial resolution to see that first 10 to 30 minutes of when a contrail is produced, making it difficult to attribute what flight caused a contrail that we're observing. And you can see here on a very busy day in a supersaturated region, with many flights, it becomes very difficult quickly to know what flight caused the contrail that we're seeing in the geostationary imagery. That's why our goal, we set out to create a comprehensive flight contrail data set using ground-based and satellite observations to solve the appearance lag and attribution issue. To do this, we're using the Global Meteor Network System, which utilizes 1,300 cameras worldwide that provide a substantial coverage of the sky. And the professor, Dr. Vita at Western University, who I've been working very closely with, is the founder of GMN. So this has allowed us to get access to these cameras worldwide and be able to run our system in tandem with meteor detections. To make these detections, I spent my entire winter break labeling these contrails in the time-lapse videos that we took from the GMN. So you can see there. We made about 5,000 images with labeled images. And then we took these labeled images and then we refined a YOLO V11, which is a segmented classification machine learning neural net. And while our evaluation metrics don't look super great, they get the job done. And part of that is because it's not our only method for making detections, since we have other ways to make an association. Another benefit of this is it is a fairly quick at making inferences. So since we have many cameras worldwide, it helps with processing these images. Putting this all together, we take the ADS-B data, which you can see there, maybe. And in the red is our GMN ground detections. And then in the white is the geostationary detections. So with this, we were able to make 100 flight contrail associations. From this, Google took that data set and was able to evaluate their own attribution models, which I think further solidifies the issue of making attribution with only geostationary satellites, and also can validate ourselves in using radiosondes, which are weather balloons on the days that were released in these locations that show the relative humidity. Road ahead, we're gonna automate this, hopefully, with detections and dry advection. So we hopefully look to further this data set and allow us to compare observations with contrail predictions worldwide. So Airbus has done a lot of effort in SAF fuel, which is low emission soot fuel. And something they've found is emitting less soot or emissions creates less condensation nuclei and can reduce the contrail impact. So that is something, but the main effort that we would like to see is if we can change the flight altitude to avoid these supersaturated regions. And then it only costs or burns a couple extra % of fuel, but cuts down potentially 50% of the aviation industry's climate impact.
All right. Next up, we have Quentin Weinberger. And he's going to be talking about reaction diffusion systems on cubic superlattices.
Hello, my name's Quinn, and my mentor is Dr. Callahan, and today I'm going to be talking about reaction diffusion systems on cubic superlattices. Just trying to find the buttons here. It is on. We got nothing. We'll use the computer if we can. Yeah. All right. So, let me get back here. First, we're going to go over what a reaction diffusion system is. Reaction diffusion systems are mathematical models that are representative of many natural phenomenon. Most commonly refers to systems where we start with certain chemicals that constantly react with each other, like you see right here. For example, we may have chemical A and chemical B that are continuously eating each other, leading to complex and interesting patterns. Like this one, this is called the brusylator, but in this research, we're going to focus on a general reaction diffusion system. So in my research, we focused on the symmetry group OZ2, which is the octahedral group, which has had extensive research done in the more basic three-dimensional models. In my research, we focus on the 3D superlattice solutions that correspond to the 24-dimensional representation of the octahedral group, which we refer to as the small rhombocube octahedron. That is this shape in the upper left here. Our system consists of 24 wave vectors pointing towards each corner of the SRCO, once again, this shape. And then our system is mathematically stated here at the bottom. In our search for stable solutions, we must first find the general axial solutions of the system. Usually a center manifold reduction is performed to isolate the critical eigenvalues. In this case, we assume that it has already been done. To find solutions invariant under our symmetry group, we use group theory and the Reynolds operator to find a full set of equivariant solutions. This picture here is a matrix representation of the set of permutations that represents our symmetry group. So each of these little black dots here is representative of one of the 24 wave vectors that you saw in the previous slide. The bottom right obviously is the identity, and then the rest of these are all ways that we can switch up these 24 wave vectors while respecting the symmetry of our group. We then mathematically induce additional symmetries. From our set of equivariant solutions, we reduce this group to find the solutions that remain invariant under our lower dimensional representations of the octahedral group. We then found the corresponding branching equations for each axial solution, which are listed here on the right-hand side. And then now that we have a set of axial solutions and branching equations, we want to find which of these solutions can be stable in our system. To do this, we create a 24 by 24 Jacobian matrix, a linearization of the system, corresponding to each axial solution and branching equation. We then solve for the eigenvalues of this matrix to find stability conditions. And once we have done that, we check to see if each of these eigenvalues can be negative at the same time. We ignore up to 3 zero values because translational symmetry necessitates their presence. If all eigenvalues can be negative at the same time, we can say that this system can show stability in our reaction diffusion system. And then here are our findings. On the left, you see the solutions that we found to be stable, as well as their corresponding branching equations. And on the right, you see our 3D plots, mathematical representations of these solutions. Each of these is a contour plot, and each contour is representative of a certain chemical concentration. It's important when you're looking at these not just to imagine it as a still picture, but to imagine it as constantly moving. For instance, the red and blue orbs on the bottom left picture here, you can imagine them gradually expanding and conforming to the green lattice shape around it. These are conditionally stable and unknown solutions. They produce Jacobian matrices that we could not solve in any reasonable amount of time or with the technology available at the school. And then here are unstable solutions. It's a little bit hard to tell, but these are two different contour plots. They differ by the angle of their columns and the relative angle of the wave vectors involved. And then so why do we study these systems? Reaction diffusion systems gives us insights into many different natural phenomenon. Systems like this have been used to better describe things like biological pattern formation, stripes on a zebra or spots on a cheetah, geological structures like layering in agates and in crystals, the spread of diseases, including the growth and spread of cancerous tumors, embryonic development, population dynamics, and the propagation of signals in the brain and neurons. And then I included a couple little graphics of reaction diffusion systems in nature here. On the bottom right, you can see mathematical representations of reaction diffusion systems and how they coincide really impressively with the patterns shown around these fish's eyes. And on the left here, you can see some lichen fungi type stuff that I found in Utah, which I included because it looks incredibly similar to the reaction diffusion system shown here on the bottom left. And I'd like to sincerely thank Dr. Callahan for his invaluable guidance, patience, and support throughout this project. And I would also like to express my gratitude to all the math, physics, and astronomy professors for sharing their time, their knowledge, and their passion, without which I would not have had the foundation to pursue this research and the confidence to continue exploring challenges ahead. Thank you very much.
Really cool talk. Could you go back to the slide? It was after you found the axial solutions, and it was like adding further symmetries. I don't remember the exact verbiage. Yeah. So when you mathematically introduce those additional symmetries and find other solutions, is this something? How do you go about doing this? Is this like analytic, or are you using like numerical methods?
So it's a little bit hard to answer that question, but it's all done in Mathematica, and essentially, I know it's not a great answer, but we do just that. We introduce additional symmetries, and that constrains the group and takes out some of the axial solutions that we found in the earlier step.
I know it's about 1 o'clock, but if you'll bear with us, we got 2 more talks. Charles, I won't butcher your last name. Charles, no, I just won't do it. Charles is going to continue the discussion of symmetry, or technically our third symmetry type talk. He's going to talk about explicit symmetry breaking of D sub n equivariant systems.
Hi, everybody. My name is Charles. I'd like to start off by thanking Dr. Callahan, my mentor, and we're going to talk about what I've been doing this semester. So to start, we're going to talk about just what a symmetry group is in general. There's a few of them that you guys have definitely seen before. So like the dihedral groups, whether or not you knew that's what they were called, it's anything that has certain number of axes of reflective or rotational symmetry. So you can see the letter A here. It can only be reflected over one axis and stay the way that it is. And so it has D1 symmetry, dihedral group 1 symmetry. And then you can see D2, this X is almost D4, but you can see it's got like a different shape on the ends here, so you can only reflect it in 2 ways. And then this square has D4, and we're going to be working with D4 throughout the rest of this talk and focusing on that. But some other examples are the cyclic groups, which I know some of you guys have seen. So like Z1 here, you can only do one 360-degree rotation. Z2 would be like half a rotation, 180 degrees. And then if you guys remember from linear, we've got O2 and SO2, just to remind us of how wonderful linear 2 was. So then talking about the different representations of these symmetry groups, what we were looking for is the irreducible representations of these groups, which is essentially, you can think about them as like basis transformations or basis vectors almost. So in D4 here, there are a few things that we can do. So we can do a dilation of D4, which means to essentially scale it, or we can look at a pseudoscalar, which we'll look at in a minute. And there's all these different ways that you can transform these symmetry groups so that they stay symmetric in some sense, but you can start to deviate from that base symmetric group in other ways. And then this here in the top right is the system that we're basing all of this on. So this is a differential system with D4 symmetry. So this here is the base representation. So if you look at just the solutions for these, is this the laser? Yeah. So essentially, we've got Z1 and Z2, which are going to be our X and Y axes here. And then we've got this parameter lambda on this axis, which you can see over here appears here. And if you imagine moving up this axis and varying lambda as you go, originally, when you've got a negative lambda, you only have this one trivial solution here. But as you reach lambda equals 0, your solutions start to branch in all different directions. And you can see these solutions here. So on this orange one here, that is the z1 equals 0. So you can see it's locked on at z1, and it goes up this way. But it does follow a parabolic shape that kind of rides along with that trivial solution. So what we're doing is essentially introducing asymmetries of these few different kinds. So G1 is the first representation here, and it is essentially a translational symmetry. And we'll see in a minute that this causes a lot of issues. Mathematica had it was like pages and pages of terms in this polynomial. And then we've got dilation, which is pretty straightforward. That's our second representation. And then pseudoscalar is definitely the most interesting, but is also the least cooperative of these representations. It's essentially something that you can rotate and it will stay symmetric, but you cannot reflect it and stay symmetric, which is what happens here. And then we've got G4 and G5, which are pretty straightforward. And then essentially this is just the process that we use to apply these symmetries that we talked about to the systems. And yeah, we'll go on to the next one so we can look at some cool pictures. So here, G2, you can see is the scaling one. So it's pretty much identical. You can see it's got that same trivial branch at the bottom, and then it comes off. Here, this is one of the pseudoscalar solutions. So you can see here's Z1 and Z2, and this is for a particular lambda. So it's kind of like a cross-section of this guy here a little bit. And you're mainly looking at these. And this here is a curve that connects all of those that we can use to characterize this solution. And then we will go here, and we can start this guy too. So these were the rectangular and rhombic asymmetries that were introduced. So you can see this one. We switch the direction of some of them, and we gain, they're no longer parabolic, they're hyperbolic in this axis. And then here you can see we've shifted some of those solutions left and right. And if you view this from above on the Z2, Z1, this is also hyperbolic. So adding in these asymmetries and characterizing those helps us to better understand physical systems that have this square symmetry, like beams or other things like that. So again, I'd like to thank Dr. Callahan, and I'll leave these pictures up while we have any questions.
The differential equations you had, nonlinear ODEs, do we think of those as solutions in actual space? Are these the solutions, or is it that you're plotting?
Yeah, so these are the solutions. Again, we can look at, these are the solutions that you have to the equations when you are working in this system. So again, we've got the Z1 and Z2 axes here, which are just these X and Y's here. And so as we vary our lambda, you get different solutions to these differential equations, which I think maybe makes the most sense when you think about it as changing this from negative to positive and this to negative to positive. You end up kind of changing the stability and things like that. So, yeah.
Thank you. We have one more speaker, and that is Isaiah Joy, talking about a quantum factoring algorithm. Thanks for hanging in there, everyone.
Hello, everybody. My name is Isaiah Joy, and today we'll be giving a quick talk on a quantum factoring algorithm known as Shor's algorithm.
Oh, it's still up. Yeah. Just wanted to close that for you.
Thank you.
And then this one back up.
Perfect. All right. All right, so before I would like to begin, I'd like to thank my fabulous mentors, Dr. Hamidi and Dr. Ismert, as I would not be here without their help today. All right, so before I begin, what is the goal of Shor's algorithm? So for, let's say, some composite number n, we want to find its non-trivial factors. And, well, why do we want to find its non-trivial factors? Well, we want to find them because we can actually break stuff like RSA encryption if we do. And really, we can there's a lot of number theory that goes on in the process, but we can simplify this process down to choosing an integer x in between 1 and n uniformly at random and finding its order mod n. Well, what do I mean by order? So in terms of group theory, we can define that for some x in our group, that the order of it is the smallest positive integer such that x to the r is identically equal to 1 mod n. All right, so now we have a few more things we need to get into. First is the quantum Fourier transform, or in my case, the discrete quantum Fourier transform, which is very similar to the classical Fourier transform, but it is instead acting on states instead of individual data points. And then here is the inverse quantum Fourier transform. All right. Now, in order to find r, we have to determine some operator u. And to do that, we're going to need some L bit, which is just going to be the binary bit representation for our integer n. And for some x, and suppose it has some order r. And we're going to define this operator to be such that when it acts on our chosen x, it will actually just permute it by some x times y mod n if y is in between the range 0 to n. And then everything else, it leaves it by itself, which actually shows that we have a permutation matrix and an identity matrix in the matrix representation for u, which is in itself unitary. But that's not the important part. What the important part is this fact is that the eigenstates of this unitary operator u actually can be represented as a linear combination that is equal to the ket1 vector. And why would we want it to be the ket1 vector? Well, the ket1 vector is very easy to it's very easy to prepare. An eigenstate is finicky and not really something that you can physically prepare well easily. All right, now we can get into the fun thing, this thing. So this is a quantum circuit that actually implements what Shor's algorithm does to find our order r. And as you can see, it's kind of decomposed into two separate registers here, one with our ket zeros and one with our ket ones. And we can see ket ones go through, we have QFT, and at the very end, those are just our measurement operators. And then you might see that inside this ket zeros with ket h, what's kind of really going on there? Well, what happens is that we get a uniform distribution for the computational basis vectors c2 to the n, which is actually how we are physically implementing our uniform randomness. All right, and in the first register, it consists of t qubits, while in the second register consists of our L qubits. And well, what do I mean by T qubits? So T is equal to this funny thing, and the epsilon in the denominator there is just with some desired threshold, which just determines how accurate we want to be with our estimation. All right, but before this QFT star gets applied, we kind of want to know, kind of like back in that diagram there, what our states actually look like. And it's this grossness. So, just kind of walk through it real quick. We have our ket u vector, which is applied, which gets us this, which with some clever rewriting and definitions of what the eigenstates are, we can get it to something that looks like almost exactly like the QFT applied to some ket SR. And then by getting rid of the QFT by applying its inverse and performing a measurement, we can actually get our S over R. And with a number theory algorithm called continued fractions, we can actually extrapolate what R is. All right, and so what I really need to do left is finish working out on my example of Shor's algorithm, and where that unitary operator is broken down into single qubit operations, as well as run it through a quantum computer through Qiskit. Any questions?
Hi. Okay. So, are there any considerations, either like theoretical or physical, that might help you determine epsilon, that threshold that you were talking about?
There are a couple. It's more so desired on how accurate you want your estimation to be, because you might not actually be able to represent your this S over R as a very it could be irrational. It could be something that's not. So we have to design our threshold just bases on how accurate we want to go out to be.
I'm a theoretical physicist for 20 years. I have no clue what that was all about. But anyway, I did see QFT. In my world, that's quantum field theory. What does that mean here?
Yes. So with the QFT, it's the quantum Fourier transform. So all it is that first part here. And the reason why that QFT is actually very important, because it's we're still doing stuff with data. What's really important is that since it's written in this ket notation, we can actually rewrite it in a way that allows it to be physically implemented as a quantum circuit, which is why having it is very useful, but it takes a lot of reworking in math that's too much to fit on one slide. Oh, so the IJK? Yeah, so what happens here is that we're taking some ket vector j, and we're summing it over from k equals 0 to n, where that e to the 2 pi I j k is actually the nth roots of unity around the unit circle in the complex plane. And we're just changing what value it's going to be at. So it's kind of starting at 0 and just slowly moving around the unit circle. That answers your question.
Thank you very much. Hey, thank you all for hanging out. Thank you all for hanging out and listening to all the talks. Let's thank all of the speakers. They did a great job. And that concludes our undergraduate research symposium. And for the space physics and astronomy majors, just a reminder that we have our annual forum tomorrow at 2 o'clock. If you can make it, there's food. Please come share your thoughts. And that's it. I'll let you go because we're way over. Have a good day.